Hello students, in this session we will do the chapter classification of elements and periodicity in properties. So to complete this chapter I need around like 2 sessions. Fine, so what we will see in this chapter is we will see the periodic table, how they are arranged, in what pattern they are arranged based on off-power principle. So we will see that understanding. So that one will be dealt. Same way, if you have element that is greater than 100, then how should I give the numbering? Okay, so how should the nomenclature be? So yeah, the basic understanding and things of that sort that will be done, which is the IUPAC nomenclature for the elements greater than atomic number 100. Got it? So below 100 we have given specific name to it, but if it was like greater than 100, so far they have found around like 108 elements, so we have names to it. If you get an element that is greater than the atomic number of 100, then you have certain way how you should name that element. So that's IUPAC nomenclature. We will do that one also. And then finally you have got that periodic trends. Okay, so you have got like 4 different terms or concepts which we will deal. Okay, so this concept will keep on repeating in upcoming chemistry chapters. Yes, especially in the organic chemistry, we'll keep on telling these 4 different concepts. So what are they? They are like atomic radius. So we should know how to understand the atomic radius for the atom, ions, okay, and then for the crystals and all those stuff. So we'll see the atomic radius. Then we will see like 2 different concepts, which is electron gain enthalpy and then ionization enthalpy, right? So those 2 stuff will be done. And then finally you have got like electronegativity. So together you have like 4 different concepts that we will see in this chapter. And then we will see the trends. How does it change, whether it is increasing or decreasing, or there is any exception based on the periodic table. Okay, so you'll call something called across the period and then the down the group. Okay, so we'll do all those stuff. Got it? For all those 4 different concepts that we are going to study. Finally, to conclude this chapter, we will see the basic strength and the acidic strength of different oxides and the hydrates. Got it? So that will be an extra part, and you get question from that extra stuff in the NEET examination. Got it? So these are something that we are going to complete in this chapter. So this chapter is moderately weightage, which means you get around like confirm you get around like 1 question. So it is highly likely that you get 2 questions in this chapter, right? So this is an moderately weightage chapter, but for sure you get 1 question. So this is one of the important chapter, and it is the foundation chapter for upcoming chemistry chapters that we are going to study, right? So first let me jump into the theory part. First we'll see the periodic table. Okay, so here you've got periodic table of the elements. So how am I actually going to arrange this element? That's what we are going to see over here. This one is actually the Mendeleev arrangement of periodic table. He was the Russian chemist. Got it? There were people before that, they had different intuition and idea of arranging the elements, but this is the successful one and it is the finalized one. Okay, so this is the final modern periodic table that we are going to study. Got it? So the way we are going to arrange this one is based on the off-power principle that we have already seen in the last chapter. Got it? So it's going to arrange in this pattern, isn't it? 1s2 s2p. So in that pattern we will study the arrangement of the elements over here. Got it? So here initially, if you look at the way we will consider this one is, so the column, okay, which means from top to down, will be considered as group. Okay, so the column, the top to down will be considered as group. Same way the horizontal one. Okay, so the horizontal one or the row will be considered as period. Got it? So the group is something that's column. Same way the period is something that's the row. Fine. So to remember this one easily, take the last letter of this word group. So the last letter of the word is something ends with p. Therefore if you just extend that last letter, so that's the group. Okay, which means it represents column. Same way if you look at the period, so the last letter over here is d, right? Just extend it in this fashion. Okay, so that's going to be the row over here, right? So to remember it without confusing, I'm just telling you this small trick. Yeah, it will be handy at times. So down the group, which means that's the column across the period. That means that's the row in this periodic table. Got it? So the way we are going to arrange this one is, you will have like S towards the left of the periodic table, S block elements, or the elements that has the final shell to be S based on the arrangement. So that will be on the left of the periodic table. Same way on the right of the periodic table, on the extreme right, you will have like you would have got P. Okay, so the element which has the final shell to be P subshell, they will be on the right. Okay, same way, yeah, same way in between you would have got the D block elements. Got it? So this thing will have the last electron to be filled in the D subshell. Okay, so that's going to be the D block element. Same way within this D block elements, obviously there is one more thing which is the F. Okay, so that F block elements will be noted separately as lanthanoid series and then the actinoid series. Okay, so it starts with lanthanum and then you would have got like 14 elements into it. Yeah, so that then the next you would have got like 14 elements into it, so that's going to be the lanthanoid series. Same way it starts with actinium and then you would have got like 14 elements into it, right? These 14 elements are actually actinoid series. Okay, so lanthanum and lanthanum actinium. Okay, after which you would have got like lanthanoid series and then the actinoid series. It's not possible to put it inside this one, therefore I'm gonna write it separately. So that's the lanthanide and then the actinide series. Got it? Yeah, it should be clear. So after that, you would have got the filling of D subshell. So that D subshell will be from hafnium and then it goes up. Got it? Yeah. So this is how we are going to arrange this one. So what we will study in chemistry is we'll study the S block elements separately. Same way we'll study the P block elements separately. And this one is called as the transition metals. Okay, transition elements, which will be in between. Yeah, that's going to be in between this stuff. Got it? The inner transition elements are these two stuff, which is lanthanoid series and then the actinoid series. Okay, so do not want to worry about the filling and filling of electrons into it, electronic configuration and all those things, because we will learn in the upcoming chapter. So that is this F block element chapter where we will do the filling of the elements based on this atomic number. We will do all the stuff in respective chapter. As if now what you need to know is this is the arrangement of the periodic table. The way we are going to arrange it is you will have the S block elements towards the extremely left, and then towards the extreme right you would have got the P block elements. In between will be the transition and then the inner transition elements. Transition elements are going to be D block elements where you would have got the lost electrons filled into the D subshell. Same way then you would have got the F block elements which would have had electrons filled in the F subshell, right? So that's how you should get this idea, right? So this is what you need to know regarding the periodic table. Now I'm going to tell you what are all the elements that you need to memorize. Okay, so you should by heart these elements. That should be at your fingertips. That's one. We would be able to get the arrangement. How does it actually relate across the across the period and down the group. So we get that increasing or decreasing order. You should know the element by heart, right? So I'll tell you what are all the elements that you need to by heart. Okay, so you have to memorize all the first 30 elements. That has to be done. Okay, whatever clue word that you're gonna make, you just make it by yourself, but you should remember all these 30 elements. Okay, so those 30 elements are obviously gonna be hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and it goes up till until zinc. Okay, so you should remember all these 30 elements. Yeah, at 11th grade you would have already memorized. Okay, by the 10th standard itself you should have memorized this 30 elements. If not, you should memorize this one. So these elements will keep on repeating, so you should know its atomic number and everything. Got it? So you have to memorize till zinc. Then what you have got is you have to memorize this one down the group, the S block elements, which will be hydrogen, lithium, okay, sodium, potassium, rubidium, cesium. Yeah, hydrogen hydrogen doesn't come into it anyway. It will generally start with lithium. Therefore, lithium, sodium, potassium, rubidium, cesium. You should know this one. Then for the 2s, you would have got like beryllium, magnesium, calcium, strontium, barium. So this is something that you need to memorize. Okay, same way you have to memorize this P block elements also. First, let me tell you how is it gonna fill. Okay, so when you look at this for period 1, okay, so the period 1 actually represents, it's going to fill in the first principal quantum number. So the first principal quantum number is like 1. So in 1 you would have got like only one subshell, that's going to be S. Got it? Same way for the 2, that's the second period, and also that's the second principal quantum number. In this, when n is equal to 2, you would have got like two subshells, that's going to be S and then the P, right? So with the case of first n equals 1, you would have got like two, you would have got like one subshell, that's S, therefore that's going to be like 1 for the hydrogen, and then the other electron will be for the helium, right? So 1s is done, which means you have got like stable configuration. Once that particular principal quantum number is completed, that's going to be the stable configuration or the noble gas configuration. Okay, so that element is going to be extremely stable, and then it will not involve in the chemical reaction unless it is at its extreme condition. Okay, under high temperature and high pressure it can undergo certain chemical reaction, but on the generalized case these are noble gas configuration and they are extremely stable. Okay, got it. So you get the noble gas configuration only if you have like completely filled p Schiff shell. When you have got completely filled p Schiff shell, that's noble gas configuration. Fine, so that is something that you need to remember. So here you have got first period, okay, at the first row, which has like 1s. So that's the structure that I've got over there. So here you've got like s and then the p. Yeah, and no, only the s, and then the principal quantum number that is needed is like 1s. So the first one of the Aufbau principle is done. After 1s, what would I have got? I would have got like 2s and then the 2p, right? If you look at the next period, obviously you should have like 2s and then the 2p, right? So this thing is done. So here it's going to be lithium, beryllium. I have told you, right? You should memorize this one. No other option is left. Lithium, beryllium, and then you would have got boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, so that's the first 10 elements. So for the first one, you have got like 2 electrons. It is done. Then you have got like octet rule, which means when the 8 electrons are filled in the outermost shell, it will be stable. Okay, so that will work out only for the second and then the third row. So here, when you consider this one, when the 8 electrons are filled, that's octet rule, which means you have got the 8 electrons which is completely filled. Therefore, you will attain noble gas configuration and the element becomes extremely stable. Got it? So the element that you need to know is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So you have got like 2 electrons filled in the 2s. Same way you have got like 6 electrons that was filled in the p. So together you have got 2 Schiff shells into it. One is like s and the other one is p. And the principal quantum number that you need to know over here is like 2. Got it? So next, after the filling of 1s, you would have got like 2s, 2p. Then you would have got 3s, 3p, 3d. But we know based on the filling of Aufbau principle, you would have got 3s, 3p, 4s, then comes the 3d, right? So here it will look something like this, which is sp. So same way, sodium, magnesium, 3s, 3p, the third row, 3s, which is like sodium and then the magnesium. Then I need the filling of p Schiff shell, which will be aluminum, silicon, phosphorus, sulfur, chlorine, argon. Okay, so this is also something that you should have memorized. Okay, horizontally, the sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. So together now we have got 6 electrons that was filled in the p Schiff shell. So even in this case, you have got 3s, 3p, right? So in the third period, you would have got 1s and then 1p. That would have been the 3 principal quantum number. Okay, so that's the third principal quantum number, right? So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Memorize it. Then now we are into the fourth period. So in this fourth period, what would I have had? I would have had 4s, then comes 3d, then comes 4p. Okay, so if you look at the period in this periodic table, always you will have the same number for the s and then the p. Okay, if you look at the d block elements, it will be one number less than that of the s and then the p. Okay, so that's how it will be. Got it? So here you have got potassium, calcium, that's going to be 4s, 4p, I mean 4s1, 4s2. So that stuff is done. Then you would have got the d Schiff shell into picture. So in the d Schiff shell, that's going to be 3d. It is like one principal quantum number less than that of the 4s. Okay, so that will get filled until zinc. Then you would have got this one: gallium, germanium, arsenic, selenium, bromine, krypton. Okay, you do not want to memorize in this fashion, but you should know group wise. Okay, so period wise is not needed. Until zinc period wise, it is mandatory that you should have memorized. Okay, if needed, you could do some extra memorization. That's not what I'm telling you. But till zinc, you should know all the first 30 elements. That is mandatory that you should have memorized. Okay, got it. Here you have got potassium, calcium, then scandium till the zinc. That gives you together like 30 elements. In this 30 element, I have included only one d Schiff shell. So that's the transition elements or the transition elements, okay, or the D block elements. Fine, that's for the 3D. Then you have got like 4p. So here, if you just look over here, you have got S, P, and then the D. Okay, so SP was 4. With the case of D, it was like 3. Yes, it should be obvious. Yeah, no doubt should be there with this case. Then let's move on to the next period, which will be 5. So here you have got rubidium. SR is going to be strontium. Okay, so rubidium and then the strontium. So if you look at these two stuff, these are like 5s obviously. Then you would have got yttrium till some Cv. Okay, so here this is like, yeah, 5s, and then this will be for the 4d. Okay, then you have got yeah, indium. Sn is actually the tin, okay, or the stannum. Yeah, tin, and then Sb is antimony. Okay, so Sb is actually antimony. Then you have got tellurium, and then iodine, xenon. Okay, so this is the p block elements over here. Fine. So obviously, if you look at this one here, also you would have got like 5s, yeah, 5p, and then 4d. Got it? So here you have got s, p, that's for the 5, and then 1d structure. Okay, so this one is for the 5 and this is for the 4. Got it? This stuff is done. Then let's move to the last two periods. Now we only have last two periods of the periodic table, which will be this period 6, isn't it? So here you've got like cesium and then the barium, which will be my S block elements. Okay, so after that you would have got like F. For F, then comes the 5D, isn't it? I've told you always the D block elements will be one principal quantum number less than that of that row. Same way with the case of the F block elements, it will be two number less. Okay, so here it starts with lanthanum. Okay, so with lanthanum the filling will be for the 5D one, then comes the 4F. Okay, so after this 6S you would have got like 4F. Okay, so while doing the F block elements, I'll tell you how does the electronic configuration actually comes. You do not want to worry about that one. So it starts with the lanthanum. So with the case of lanthanum, that's gonna be like 5D1. After that, that electron will just fill in the F block elements, okay, in the F subshell. So you would have got like 14 elements next to it. So it starts with cerium and then it ends with lutetium. Okay, so it starts with cerium and then it ends with lutetium. So this will be the bridging element, which is like lanthanum. So that series is called as lanthanoid series. Got it? So after the completion of 4F, so you would have got like 14 elements over here. So after the completion of 4F, then you would have got the filling of 5D, isn't it? That's going to be one number less than that of the 6. Therefore, it should be like 5D. So it goes like hafnium and then it goes on. So after that, after the completion of this D transition elements, then you would have got the P block elements. Okay, so that's like tellurium, lead, and all those stuff. Got it? So this P block elements will be 6p, right? So here you have got 6s, 6p subshell. Then you have got like 4f subshell. Same way you have got like 5d subshell. Got it? So that's how it's gonna be. So if I want to put it over here, you would have got like S, P, those two stuff are same, D, and then finally you would have got F, isn't it? So here, if you have to write this one, this is going to be 6 and this one is 5, this one is 4. Okay, if you look at the numbers for the arrangement of the subshells, it will be 6s. So that's how it's going to start. One number less than that, which is like 5d, two number less than that, that will be like 4f. Okay, now we are into the last period of this periodic table, which will be 7. So that's 7s, right? So francium and then the radium. Okay, so from this point on, the radioactive elements will start. So francium and then the radium. So here that's the S block elements. After that one, you have got like actinium. So that's why it is called as actinoid series. It's 7s, one number less than that, which will be like 6d. So that's where the next element is going to fill. Next electron is going to fill. After the actinium, you'll have start filling of F elements, F subshell. Okay, so you would have got like 14 elements into it because you have got 7 orbitals. Therefore, that will be the next 14 elements. It starts with thorium and then it ends with LR. Okay, so that's the Lawrentium. Okay, so this is lutetium and this is Lawrentium. Okay, so that's actinoid series. The above one is the lanthanoid series. Same way for the actinoid series, actinium will be the bridging element. Okay, for the D and then the F. So these two elements are actually the inner transition elements. Okay, so this series is called as inner transitions series. Okay, yeah, this is transition elements and this is like inner transition elements. Got it? So then after actinium you have the elements as usual filled. Then after this one you would have got the P, the final P subshell that was needed over there. So that's going to be this one. S, yeah, that's going to be S, P, D, and then the F. Okay. See, for this you have got like 7S and 7P. Then for the D you would have got one number less than that, which is 6, and then the final, which one is 5F. Okay. So this is what you just need to know regarding the periodic table. As I've told you, you have to remember first 30 elements. Same way, you have to know the S block elements. You have to by heart it. It has to be memorized. Okay, lithium, sodium, potassium, rubidium, cesium. Same way, beryllium, magnesium, calcium, strontium, barium, radium. Okay, this stuff has to be memorized. Then this entire group for the P block elements should be memorized. Okay, the for the P group 13, you have got this shortcut which you could acronym which you could actually remember it, bag it. Okay, so boron, aluminum, gallium, indium, thallium. Okay, so I've just matched with the first letter. So boron, aluminum, gallium, indium, thallium. Then for this one it's going to be carbon, semiconductors, silicon, germanium. So carbon, silicon, germanium, tin, lead. Okay, then you would have got the nitrogen family, which is carbon, nitrogen family. For the nitrogen family, it's like nitrogen, phosphorus, arsenic, antimony, bismuth. Okay, do not want to worry about this last one. That's not going to come because these are radioactive elements. Do not want to worry about this last element. So till bismuth, it's fine. Then you would have got like oxygen family, which is like oxygen, sulfur, selenium, tellurium, and then the polonium. Then you have got the halogens and then the noble gas. Okay, so the halogen is fluorine, chlorine, bromine, iodine, argon. You might have already memorized this one in the lower grades. Same way it goes for the noble gas: helium, neon, argon, krypton, xenon, radon. Okay, so if you have done your lower grades well, you should have already known 30 elements. Same way you would have known these S block elements. Same way you would have known this halogen and then the noble gas elements. Only stuff that would have been left for you to memorize will be this boron family. For that I have given you the acronym, which will be BAGIT: boron, aluminum, gallium, indium, thallium. So the only stuff that would have been left should be like carbon family, nitrogen family, and then the oxygen family. Okay, carbon, silicon, germanium, tin, lead, sodium, nitrogen, phosphorus, arsenic, antimony, bismuth, oxygen, sulfur, selenium, tellurium, and then the polonium. Okay, you could remember it in this fashion: oxygen, and then comes S sulfur, STP. Okay, standard temperature and pressure, something of that sort. Selenium, tellurium, and then the polonium. Okay, oxygen, sulfur, selenium, tellurium, polonium. Okay, so this is what you should memorize out of all the elements that I've told you in this periodic table. Okay, so you should know how does it actually electron fills. So you have got like one S, that's the first one, first first period. Then you have got like two periods which just has the S and then the P subshell. Then you have got like two period which has S, P, and then the D subshell. Then you have got the last two period which has S, P, D, and F. Always in a period, if you get some principal quantum number, one number less will be for the D subshell, two number less will be for the F subshell. Okay, so that's what you need to know. Here I've just written for an element, I'm just going to write the electronic configuration. That should be obvious, which is for the sodium. Okay, so where do you have the sodium? That's going to be the third period, isn't it? Yeah, it comes after the noble gas configuration of the neon. Okay, so the neon will be for the 10, then it comes after that one. Okay, so if you have to write that one for the 11, you should have already known this one. Got it? See, as far as this F block element is concerned, I haven't told you how does it actually fill, how does it partially get filled, then how does it completely fill. That's not what I've told you. Okay, while doing F block elements in the 12th standard, you will get to know that stuff. Okay, so that's a simple one. Anyway, we can learn that one in the 12th grade. Okay, So as if 30 elements, 40 elements, you should know how to fill those electronic configuration. Okay. So here for the sodium, I'm just going to put the electronic configuration. How should it actually be? You would have got like 1s, 2, and then you would have got 2s2, then you would have got like 2p6. Now I have just filled the first 10 elements, then you would have got the final one, which will be the 3s1, isn't it? So the next one is going to be 3s1. Okay, so you have got 1s2, 2s2, 2p6, and then the 3s1. Okay, or else how I could actually write this one? I can put the noble gas element, and then I can fill the in the last subshell. Okay, so here the last subshell is going to be the 3s1. So up to 2p6 you have got the noble gas of neon. Okay, so that's the element before that one. So the noble gas configuration, for which I'm going to choose the noble gas, that's going to be neon. Then you have got 3s1. Either you could write it in this fashion or in this fashion. We are just only worried about the outer electron that has been filled in the last subshell. Okay, so this is what is meant by outer electrons. Okay, or the valence electrons. Valence electron, outer electrons. I'll use those two stuff alternatively. Got it. So this is what you need to know regarding the electronic configuration or electronic arrangement in the periodic table. Next, we will see the nomenclature of elements for the atomic number greater than 100. Got it? So you need to have like 3 numbers in the atomic number. If that was the case, how should I actually name those elements? That's what we are going to see. So that's IUPAC nomenclature of elements. Fine. As if now 108 elements has been found. Got it? So we have named all those elements. If we find element which has atomic number greater than 120, 130, something like that, then how should I give name to it? That's what we are going to see now. It is, those elements are going to be unstable anyway. It will disintegrate into two daughter nuclei which will have an atomic number that's going to be less than 100. But if such an radioactive element or highly unstable nucleus is found, then how should I name that element? That's what we are going to see. Got it? So that's IUPAC nomenclature of element. How should I name it? Anyway, those numbers will be between 0 to 9, isn't it? Let me give the convention that we stick to. For the 0, that's going to be nil. Okay. And then for the 1, it's and. Got it? And then for the 2, that's going to be bi. Yeah. Then for the 3, that's tri. And then for the 4, it's going to be quad. Okay. So this is how I'm just going to name it. So the symbol that I'm going to give will be the first letter of this word. So the first letter of these words are N, and then for the N it's going to be U, and then for the bi that's like B, for the tri that's T, and then for the quad that's Q. Okay, now I have given the symbols for the name that I've chosen. Same way with the case of 5, 6, 7, 8, 9, that's going to be for the 5, that's like pent. Yeah, and then for the 6 it's like hex, for the 7 it's sept, for the 8 it's oct, and then for the 9 it's n. Okay, same way the symbol that I'm going to choose will be the first letter. For the pent it will be P, for the hex that's going to be H, for the sept it's like S, and then oct O, and then the n that's E. Got it? So these are the words that I've chosen. These are the terms that I've chosen, which is like nil and bi, tri, quad, NUBTQ. So these symbols will not repeat. So you will have like different alphabets to all the 10 numbers from 0 to 9. PHSOE. Got it? So you have to memorize this one. You should know by heart, right? So in the next page, we are going to see how to use these terms to get to get an to get the name for that element. If it was like 101, how should I actually combine these terms to get that element name? Got it? That we will see in the next page. Fine. So here you have got nomenclature of elements with atomic number above 100, right? So I have typed already all those names. Got it? So this is just a simple one. If you have got like atomic number 101, 102, 103, 104, how should I actually name it? We know for the 1 that's going to be N. Okay, so N. Then for the 0 it's nil, and then again you have got like 1, so that's going to be un, null, and em. Got it? Un, null, and em. So here, whatever the element it is, you'll have to end it with em, em, em. Okay, so that's the convention for, okay, so un, null, and em, and then for the 102 you would have got un, null by em. Yes, right. Same way for the 103, it's gonna be un, null, tri-em, and then it goes on un, null, quad-em, quad-em, quadrium, and then pentium, hexium, septium. This is how it goes on. Fine. So if it was 110, then what it would be? It would be null. I mean nullium. Got it? Then for 111, that's gonna be unnium. Got it? That's how you have to name these elements. So it just goes on. You can make n number of elements out of it. That's not a thing over here because I've just given every term for all those numbers over there, right? So this is how the nomenclature is done for the element greater than 100. Got it? If you find any element that has an atomic number like 150, now you can give name to it. You do not want to choose some random name and then give it to it. You have certain nomenclature to which I can stick to. Got it? So this is what is meant by nomenclature of elements. Got it? Now I have given you the IUPAC standard convention. The symbol is obviously the first letter, isn't it? So that's going to be UNU. The first letter of the symbol has to be capital. That too is a convention, so it has to be UNU. The first one has to be capital, unnull, unem. And then for the unnull by em, it's going to be UNV. Got it? So this is how you need to give the symbol. It has to be obvious. Then comes this one, which is the official name that we have given. So up to 118 element, we have chosen the name and we have already fixed certain, in the honor of certain scientists, we have fixed those name to it. For 101, the guy, the scientist, the physics chemist who worked on the periodic table, I have to honor him, we have given the name Mendelevium. Okay, and then you've got like Nobelium, Lawrencium, and it goes on, right? So here the thing is you have to memorize all these 118 elements because one of the time in the NEET examination I've asked this question. So they what they did is they gave this IUPAC official name, or they are given something like Seaborgium or Borium, and then they asked us to find the symbol for this name. Only if you know this by heart, you will be able to get the symbol, isn't it? That is when you'll know this atomic number. From that, you could actually get the symbol. Instead of giving the atomic number, what they did is they gave you the IUPAC official name. So, for example, if they give you like Hassium, you should know that's going to be like 108. That is when you'll be able to mark this symbol UNO. So here you have to memorize this element from 101 to 108 because in one of the NEET examinations they have asked such a question where they gave you the IUPAC official name and they asked us to find the symbol for it. Got it? Only if you have known this one by heart, you would be able to get this symbol, isn't it? Same way, once you by heart this one, this symbol, this IUPAC symbol becomes easy, right? So that's going to be the straight match. Mendelevium MD, Nobelium NO, Lawrencium LRN, things of that sort, it goes on, right? So here what I'm going to tell you is you have to memorize this IUPAC official name till 118 because they have asked such question in one of the NEET examinations. Got it? Yeah, whatever acronym that you're going to choose or whatever pattern that you're going to follow, whatever it is, you have to memorize it, right? Yeah, this is what you need to know regarding the nomenclature of elements for the atomic number above 100, right? You should be clear with the nomenclature that I've done. Same way, you should have a clear understanding of how I have arranged the periodic table and all those things. Now, next, we are going to see the periodic trends. The first one, that's the atomic radius. Now, we'll see the first one of the periodic trends, which is going to be atomic radius. Got it? See, here I have typed all those things that are needed. Got it? Only thing that is left is for me to explain you whatever I have written over here. Fine. So it will be very simple. Only thing is you just need to know the basic and the clear understanding of atomic radius in different situations. So that will be easy. So in this session, we will see only the first two terms, which is atomic radius and then the ionization enthalpy. So electron gain enthalpy, electron negativity, and other stuff will be seen in the next session. Got it? So we'll see the first two terms that are needed to know the periodic trends in the periodic table. Got it? So the first one is the atomic radius. So it's obvious. It's the radius of the atom. That's going to be the atomic radius, isn't it? That's the statement that I've written over here. The distance between the center of the nucleus and the outermost shell where the electrons are present. Okay, so the distance from the center to the outermost shell or the valence shell. that gives you the atomic radius. Got it? So bond length are measured using X-ray diffraction, electron diffraction, and then the infrared spectroscopy. So you will learn what is meant by diffraction in your 12th grade of the physics class. Got it? So diffraction actually means when something is gonna hit a corner, it bends and then it scatters. Got it? So that phenomena is known as diffraction. So it will happen when you have that space that's going to match with the wavelength, there will be a diffraction over there. Got it? So that should be an empty space, and then the bend should be matching with that of the wavelength of the light that's going to pass through it. In that situation, you'll have diffraction that's going to happen. We will see that one clearly in detail in the 12th grade of the physics. Got it? Do not want to worry about that one as if now, but you do some experiment to get this atomic radius. Because it's such a tiny quantity, I'll use light. The wavelength of that light will match with the space between those two atoms, which will be responsible for the diffraction of that light. Got it? So bond length are measured by some experiment, which is like X-ray diffraction. Electron can also behave as wave. Got it? So that's electron and infrared spectroscopy, right? Based on all those studies, I'll be able to get the atomic radius. Got it? So how should I actually consider with the case of ions, with the case of covalent bonded element, and then with the crystal, all those things we'll see now. So first we will see the covalent radius. So when you have like covalent bond between two atoms, that's there you will have like covalent radius. Got it? In nature, that is how those elements are going to exist. Therefore, we are left with no other choice. We have to get the covalent radius. So those covalent bond, ionic bond, and all those things, as if now, based on the 10th grade, you have some understanding, right? That's enough. The next chapter is going to be chemical bonding and molecular structure, where we will learn in detail regarding the covalent ionic bond and all those stuff, right? As of now, those basic understanding is good enough for this class. Got it? So covalent bond actually means you are going to have the sharing of electrons, isn't it? So half the distance between two nuclei of two like atoms, like H2, that's going to have the covalent bond. So if that's the case, it always exists in nature in bonded state, in diatomic state. Oxygen, it exists in diatomic state. Nitrogen, it exists in diatomic state. If that's the case, then half the distance of two nuclei of two like atoms bonded together by a single covalent bond. So the bond over there should be like single covalent bond. With the case of oxygen, there's going to be a double bond, so it will get deeply bonded. So you shouldn't consider that to be an radius, because there you have a like deep connection between those two oxygen. So obviously the length is going to be less. Okay, so one of the condition that has to be verified is single covalent bond. With the case of hydrogen, you will have like single covalent bond, so the bond will be single bond. With the case of oxygen, you're going to have the double bond. Okay, so obviously that's going to be much more less when compared to that of the atomic radius. Same way for the nitrogen, you're going to have three bonds. So with the case of oxygen and nitrogen, that's not how I measure the radius, but with the case of hydrogen, that's a good approximation that I'm going to do, right? So you just take two hydrogen atom, bonded hydrogen atom, and half of the distance between these two nucleus will give you the atomic radius. That's what they are given over here. Okay, one thing is very important, which is the bond between them has to be a single covalent bond. Got it? Half the distance between two nuclei of two like atoms bonded together by a single covalent bond. Next, let me see how to find the covalent radius for heterogeneous atom. Here you have got in heterogeneous atoms, knowing the bond length and covalent radius of one atom. So if you know the covalent radius of one of the atom, for example hydrogen, you can actually get the radius of the other atom. Just subtract it, you'll end up getting the radius of the other atom, right? Here, these two atoms are same, therefore I just split it symmetrically, divided by 2 gave me the atomic radius or the covalent radius, whatever it is. If it was like heterogeneous atom, let me take the situation for the nitrogen. Okay, you take ammonia, where you have got like one N and then the 3 hydrogen. I obviously know the covalent radius of the hydrogen, right? If you get the bond length between nitrogen and then the hydrogen, okay, it is bonded singly. Okay, you have single bond into it. So if that was the case, then obviously if you know the if you know the atomic radius of hydrogen, then the leftover distance will be the atomic radius of the nitrogen, right? Those two are in single bond, by the way. By that, I'll be able to calculate the atomic radius of other heterogeneous atoms, because if you take like N2, there will be like triple bond into it. I wouldn't be able to consider that one as the atomic radius. Therefore, I have to take an heterogeneous atom which has been bonded to such atoms like hydrogen. There are multiple atoms other than that also, but in this situation, I have taken hydrogen. So if it is bonded to hydrogen in this fashion, from that, I'll be able to get the bond length of the I'll be able to get the atomic radius of this heterogeneous atom. For example, nitrogen. That's what I've discussed over here. So here the statement is clearly stated that in heterogeneous atom, knowing the bond length and covalent radius of one of the atoms, the radius of the other atom can be determined. Because if you know one of the atom, just subtract it, leftover length is going to be the atomic radius of that different atom over there. Got it? For example, nitrogen. So then you have got covalent radius is used for non-metals, because non-metals always exist in nature, most probably in the gaseous state, okay, most likely in the gaseous state. Therefore, it will also be in diatomic or triatomic state. So in that situation, covalent radius will be the best way to find the atomic radius of those elements. Got it? So for non-metals, radius is the only possibility that we have got, right? Then comes the crystal. So in the crystal structure, all the metals that exist in crystal, isn't it? Sodium, magnesium, and then potassium, calcium, whatever it is, they exist in metallic state. Okay, so this S block elements that has more metallic nature into it. So in the nature they exist as crystal. Okay, so we will learn how this crystal is formed with the ion, with the with the nature of ion and all those things in the next chapter. As if now, for these ionic compound, metallic crystals, aluminum, whatever it is, D block elements, all those stuff will have like metallic nature into it. So this is the first understanding that you need to know. Towards the left, you have got like S block elements, which has more metallic nature into it. Towards the right, you have got P block elements, which is non-metallic in nature. All those noble gas, hydrogen, helium, yeah, all those halogens, they are non-metallic in nature. Got it? So towards the extreme left, you would have got metallic nature elements. Towards the extreme right, you would have got like non-metal elements. Got it? So to get the atomic radius of non-metal, I am just left with no other option, only to find the covalent radius. Got it? So with the case of metals, you have got like crystal radius, that's going to be half the distance between the nuclei of two adjacent metal atoms. So in the nature, it will exist in crystal structure. So half the distance will give you the crystal radius. Do the same X-ray diffraction, electron diffraction, whatever it is, and get this distance. So half the distance between the two nuclei of two adjacent metal atoms in metallic closed packed crystal lattice. So it exists in crystal structure. Okay, so we will learn more about crystal in the 12th grade. That's going to be this chapter solid state. Got it? Then you have got, it is also known as metallic radius. So crystal radius is also known as metallic radius. Finally, crystal radius is used for the metals. Got it? For the metals, this is the only way how I could actually find the crystal radius. In the next page, you have got like van der Waals radius. What is meant by van der Waals radius? See, this one we will use when you have the configuration of noble gas. Okay, so for all the noble gas elements, I'm just left with no other choice. I'll have to get the van der Waals radius, because these two noble gases, they will never get bonded. They'll always be single, because that in and itself is stable. Therefore, no bond is needed. Only under extreme situation, there is the possibility of this slight bonding. But when it comes to the environment condition, there wouldn't be any bond between those noble gases. Got it? So in those cases, I'm just left with no other choice. When it is stable, it is always single. Therefore, I'll have to get the space between two neighboring atoms. Okay, so once I get the space between those two neighboring atoms, half of that distance will give me the van der Waals radius. So it should be obvious. This van der Waals radius will always be comparatively greater when compared to the crystal radius and then the covalent radius, because there you have had certain bond. When you got like sodium crystals, if you take the sodium solid, it will be in the solid state there, and also it will be in the crystalline structure. Okay, so there was this close attraction between two different sodium metal, and it was staying close to each other. Okay, there was this attraction. Got it? But in this situation where you are going to find the van der Waals radius, these two atoms are just freely moving in the space and the force is very weak. Okay, so here half of that distance will be greater when compared to that of the covalent radius and then the crystal radius, but you're left with no other choice. This is how I'll have to get the atomic radius of the noble gas. Got it? Let me read the statement that I've given over here. You have got half the distance between the nuclei of two non-bonded neighboring atoms. Okay, so half the distance between these two are not bonded. Okay, of two adjacent molecules in a solid state. So that gives you the van der Waals radius, right? If I have to get the solid of the helium, I'll have to freeze it, which means I'll have to bring it very close to 0 Kelvin. Got it? Somewhere around 10 Kelvin, 14 Kelvin, things of that low temperature. I'll end up getting the solid state of the helium nucleus. When you get that solid state of that helium, I can do like X-ray diffraction and all those experiments, and I'll end up getting the van der Waals radius. It should be obvious. This is actually not the exact bond that you have between those two atoms, because it in and itself is actually spaciously arranged. There wasn't any sharing of electrons of things of that nature, right? Therefore, here this van der Waals radius will be comparatively greater when compared to that of the crystal radius and then the covalent radius. Got it? You should be okay with this order that I've written over here. So here you have got like van der Waals radius, which has a greater radius because this is between the two neighboring atom. Got it? And then and then I frozen it to very low temperature to make it into a solid state, and I did the experiment. Therefore, this is between two neighboring atoms. With the case of crystal radius, this exists in nature in the solid state, right? So there was some bond between those two atoms. Therefore, it should be much closer. So here it's the crystal radius, example aluminum, sodium, magnesium, whatever it is. Then you have got like covalent radius. So here the covalent radius will be much lesser when compared to this van der Waals radius and then the crystal radius, because here you have got like sharing of electrons. So one electron will be shared between those two atoms. So got it? So one electron from one atom and one electron from one atom will get shared. And then the closeness is much more greater when compared to these two situations. So in the case of van der Waals radius, there wasn't any bond. Just I have frozen it and made the atoms to come close to each other. So that's a kind of neighboring atom. With the case of crystal radius, in the nature it exists in crystal, right? There wasn't any sharing, but still you had some bond between it. Therefore, that's going to be the crystal radius, metallic radius. Then finally, you have got the covalent radius, yeah, which has like much more shorter atomic radius. Got it? Yeah. So this is how we find atomic radius for the different element. So based on the availability in the nature, we just find a pattern to get the atomic radius of all those elements. Fine. So here I've written one more statement. For simplicity, we may use the term atomic radius for both covalent and crystal metallic radius. You're left with no other choice. Whether it is a crystal or covalent, however it exists in nature, it doesn't matter. I'll just call simply as atomic radius, depending on whether the element is a non-metal or metal. Okay, if I just tell you atomic radius, you have to take it as such. You do not want to worry about whether it is a crystal or whether it is a non-metal. Do not want to worry about anything. Just take it as atomic radius. Fine. However, the atomic radii of inert gas are usually expressed in terms of van der Waals radii, because this one, they never share anything between them. They in and itself is stable, right? Therefore, they do not form any chemical compound. That's the reason why I'm telling you this inert gas have much more greater atomic radius when compared to other element than expected. Okay. So, however, the atomic radii of inert gas are usually expressed in terms of van der Waals radii, as they do not form any chemical compound, right? It has to be clear. You shouldn't have any doubt. Then here, let me let me write the increasing or decreasing order. So here you have got lithium. So this is the second period, isn't it? I've taken the second period and then the third period. Second period is going to be lithium, beryllium, boron. Okay. So with the case of lithium, obviously 1s is completely full and the first electron is filled in the 2s. Got it? First 2s electrons is filled. Then here you have got like 2 electrons filled in the beryllium. So if you consider the net attraction given by this positive charge, it's going to be the 3 positive charge that's going to pull this one in. But if you consider over here, you have got like 4 positive charge, it's going to pull like 2 electrons. So 4 positive charge is going to pull the 2 electron. Therefore, this would have shrunk a little bit when compared to this one. Therefore, the atomic radius decreases across the period. Okay, it's going to shrink it, right? Therefore, the atomic radius of lithium should be greater. Yeah, it should be greater than compares the beryllium, because it got shrunk because of this lithium. And then finally you are going to have the boron, which is much more shrunk when compared to the beryllium. Got it? So this is how you will have this is the trend of the atomic radius across the period. So when you're going to do the experiment, we will expect in this fashion: lithium should have greater atomic radius, and the beryllium should have a little bit less atomic radius when compared to that of the lithium. Then the same in the same shell, I have got the boron, isn't it? I mean, in the same principal quantum number, I have got the boron, right? So that is filled in the p shell. So that's why I've put double shape over here. So only one of the electron is filled over there, right? Next, let me match it with down the group. If I have to match it with down the group, obviously here in this situation, the next electron is gonna fill after the filling of the 10 electrons. So that's the 11th electron that got filled in the boron. Okay, so you have got like 11 positive charge and another 11 electron. Here gonna go into the completely different shell. Got it? So that's gonna be the outer one, extremely outer one, isn't it? Therefore, when you compare this lithium and then the sodium, it got filled in the 2s subshell. Here it is going to get filled in the 3s subshell. Therefore, obviously, this should have much more greater atomic radius when compared to the of this lithium. Therefore, down the group, atomic radius actually increases because it is getting filled in the next principal quantum number, right? Therefore, here the atomic radius of sodium is greater when compared to that of lithium. Same way, the atomic radius of magnesium is greater when compared to that of the beryllium. Here also it is greater. Got it? Across the period, the atomic radius decreases. Down the group, the atomic radius increases. Then it has to be same with the case of sodium, magnesium, and aluminum, isn't it? Therefore, here also you would have got sodium, which has the greater atomic radius when compared to magnesium, and the magnesium has the greater atomic radius when compared to that of the aluminum, right? So this is how you are going to have the you are going to have the periodic trends of the atomic radius with respect to across the period and then the down the group, right? It has to be clear, no doubt should be there so far. Here I have written all the statements that I have already explained to you with respect to the trends. So here I've got, as we move along the period, effective nuclear charge increases. Yes, when compared to lithium, beryllium had more effective charge into it, right? Increases, therefore atomic radii decreases. Okay, so I've told you, right? So this is the reason why it got shrunk more when compared to that of the lithium. So atomic radius is actually inversely proportional to the effective nuclear charge. If effective nuclear charge increases, then obviously atomic radius decreases. Okay, just remember this one. You do not want to worry about this number. Okay, so what I've done over here is what I've given over here is lithium, beryllium, boron, carbon, nitrogen, oxygen. I've just taken the second period and then I've given you the atomic radius. Okay, so the atomic radius over here is something like this: 1.23, 0.89. It just decreased proportionally, right? So here Z is the atomic number and this is sigma is actually the shielding effect. So how much it got shielded, leftover will be the effective nuclear charge. Already you have got like you have got like three protons into it and the effective shielding was like 1.7, so left over, so that was a shielding, which means that inner electron, you have got like 1s electron, right? So that inner electron will shield 1.7 of its impact and then you would have got like 1.3 proton effect on that one electron. But with the case of beryllium, I've told you, right, there are like four protons into it. Some of the in a positive charge would have been shielded by that inner electron, leftover would be like 1.95. So now we have got like more impact on that outermost electron, therefore that's going to shrink that shrink that element. So obviously you have got like 0.89 atomic radius, right? Do not want to worry about this number, right? This is something that I've taken directly from the internet and I've given you. They wouldn't ask you anything regarding this number. What you need to know is this atomic radius will decrease, right? Obviously when I verify it, do not want to worry about that whether it is a metal or non-metal, that doesn't matter. Okay, whatever experiment we do, we have a different pattern to measure it for the crystal and then we have some pattern to measure it for the covalent radius and all those stuff. Okay, whatever the stuff that we do, we end up getting the atomic radius, isn't it? When you look at the radius, it is obvious the atomic radius is decreasing. So the pattern that I expected is verified while doing the experiment. Got it? Yeah, but there's this one exception. I didn't give you the last element, which is the neon, right? The reason is because that's going to have the noble gas configuration. Generally, noble gas, how will I actually measure its atomic radius? I'm left with no other choice. I just have to measure it with the van der Waals radius. Okay, so that van der Waals radius is going to be generally greater when compared to this fluorine. Okay, it's not going to be greater than some other element, some 2-3 elements I had up before it, but it's gonna be greater when compared to that of the halogen, right? That's what I've given over here. As the noble gas elements do not form chemical bonds, it will always be single, right? It will be in monoatomic state. Their van der Waals radii are considered to be their atomic radii. I'm left with no other choice. Therefore, I'm gonna take their van der Waals radii as their atomic radii. Therefore, atomic radii of the noble gases are always greater when compared to that of the halogens. So when compared to halogen, this noble gas radii is going to be greater. Got it? So if you're going to compare the radius between that halogen, which is like one element before to that of the noble gas, that will have greater atomic radius because I have no clue to get the atomic radius of noble gas. Only way is to get its van der Waals radius, which is obviously going to be greater, right? That's what I've written over here. You shouldn't have any confusion over the statement. It has to be clear. Then you have got this one more exception to it, which is the lanthanide contraction. I've told you while seeing this periodic elements. I'm just going to tell you one more time. So here you've got this element which is like yttrium, lanthanum, zirconium, and then the hafnium. Okay, so here you have got down the group, right? So here it's like down the group. What should happen down the group? The atomic radius has to increase, right? So lanthanum should have greater atomic radius when compared to that of yttrium. Same way, zirconium, I mean, yeah, correct. Lanthanum should have greater when compared to that of the yttrium. Same way, hafnium should have greater atomic radius when compared to that of the zirconium, right? That's what we expected because this is down the group. It is filling entirely with the new shells, right? But if you look at the result, that's not how it's gonna be. See here, if you look, scandium, it's like 1.64. Next comes the yttrium, that's going to be down to it, which is 1.82. Yeah, that's a good thing. Then with the case of lanthanum, yeah, that's greater, which is 1.87. But if you just look at the exact next element, titanium, that's going to be 1.47, fine. Then you have got these two stuff, which is like 1.60 for the zirconium. If you look at the hafnium, that's going to be less. So this is odd, isn't it? The reason why is because you have got like 14 elements in between it, in between those set. So that F series subshell will just shrink it more to it such that when you get to the hafnium, you are going to have lesser number atomic radii when compared to that of the zirconium, right? I'll just show you in the periodic table itself. It will become pretty more clear. So here you've got this one, which is yttrium, lanthanum, zirconium, hafnium. What we expected for hafnium is a greater atomic radius when compared to the zirconium, right? But if you look, hafnium has lesser atomic radius when compared to zirconium. That seems to be odd. That's how it's not supposed to be. But the reason is because you have got like 14 electrons filled in the F subshell. So these 14 electrons is going to compress it again to such an extent that hafnium has less atomic radius when compared to that of the zirconium, right? So before that, you have got like 14 electrons added to it. Same with 14 protons extra added to it. Therefore, this lanthanide, there is this one more series into it, which is going to compress that atomic radius. So when you compare the zirconium and then the hafnium has less atomic radius when compared to that of zirconium. So this is what is meant by lanthanide contraction. This is something that you need to know. Okay. Yeah, they will ask you a question. One of the time they have asked you this question. Okay. So scandium, yttrium, lanthanum. This is something what we expected. So 1.64, 1.82, 1.87. It is proportionally increasing down the group. But if you look over here, it increased, then it suddenly got decreased. That's not how it should be. The reason is because of the lanthanide contraction. So you are having that 14 element that is hidden between this lanthanum and then the hafnium. So that is the lanthanide series, right? Okay, so this is the exception that you need to know with the case of 4F series. Then here comes the final thing, which is what is happening across the period. Across the period, the atomic radius decreases. Down the group, the atomic radius increases. If I don't give you the term atomic radius, then it has to be the size. Okay, so across the period, size decreases. Down the group, the size increases. Okay, right? This one has to be clear. Then we are into the final thing of this atomic radius, which is going to be ionic radius. This is something different. So what is meant by ionic radius? That's what we are going to see now. So when sodium exists in nature as a metal, that will consider as a crystal. So while measuring the distance between them, it is called as crystal radius. Same sodium, if it exists in in heterogeneous state, which means it is going to combine with some other atom, for example NaCl, common salt. So in that situation, it will exist as Na plus ion and then Cl minus ion. Okay, so you would have got these two ions in that crystal structure. Once you dissolve it in the water, yeah, the situation will be favorable. Therefore, Na plus ion and Cl minus ions will dissolve into the water, and then it will be in the ionic state inside the water. Okay, we will do that one. Anyway, this is what is meant by ionic radius. When you have got ions, how will the radius of that ion be? That's what I need to get over here. So generally the ion will exist in the electrolyte, okay, in the solution state. Fine. So distance between the nucleus and the outermost shell of an ion, okay, it should be like Na plus or Cl minus, okay, Mg2 plus, something like that. So this is not atom. It is existing in ionic state, which means I have removed one of the electrons from it, or I have added one of the electrons to it. If that's going to be the case, that is called as ionic radius. Got it? So atomic radius and then the ionic radius. These two are, yeah, these two will exist. Sodium, if I tell you the atomic radius of sodium, which means 11 electrons are completely filled and it is stable. So that's the atomic radius. If I remove one electron from it and then you have got like Na plus, that's called as ionic radii. Got it? So distance between the nucleus and then the outermost shell of an ion is called as ionic radii. They are related to the ions present in ionic solids. Yeah, I've told you, right? When it exists in crystal state, Na plus and Cl minus ion, these two stuff will be in the ionic state, right? Got it? Now I just need to get its radius. How will the radius be related? That's what I need to get over here. If you take the cation, that's going to be smaller than its parent atomic radius, because cation is going to be positive. I have removed one of the electron, therefore the positive charge is still that 11, therefore it's going to shrink that atom to much more greater extent. Okay, so the radius of the cation or positive ion will always be smaller, okay, will always be smaller than that of the parent atom or its atomic radius. Got it? With the case of negative ion, how will it be? I'm just going to add extra one electron to it, therefore here the electron is going to dominate. Got it? So this one will just bulge a little bit extra when compared to that of the parent atom. Exact other way around. Therefore here the radius of an ion, negative ion, is always larger than that of the parent atom. That's what you're going to get over here, right? Fine. So now I'm just going to compare it with some of the ions and then the anions and then the cation. Okay, here I'm just going to choose oxygen, fluorine, sodium, magnesium. I'm just going to leave this neon because that is stable electronic configuration. Ionizing that one is not possible. Okay, so here I'm just going to choose sodium and magnesium with the case of cation. If I have to ionize it, what will I get? I'll get cation Na plus, because these are more metallic in nature. So generally metallic, yeah, usually metallic compounds will be as cation. Okay, anion will be those p block elements. Okay, so non-metals will be in anionic state. So here I've got like Na plus, Mg. I can remove two electrons, isn't it, from the valence shell. So Na plus and then the Mg2 plus. Then you have got for the anion, I've told you, right, I'm going to take oxygen, fluorine. I'll leave the neon. Therefore, you would have got O2, O2 minus, and then for the fluorine, you would have got F minus. Got it? Here, if you look at all, if you count the number of electrons over here, oxygen then generally will have 8 electrons into it. I'm going to add extra 2 electrons to it, right? So 8 plus 2 gives you total of 10 electron in this case. Same way, if you look at the fluorine, you would have got like 9 electrons for the stable fluorine. Adding one more electron to it will give you 10 electrons. Okay, here you have got like 11 electrons. I have removed one of the electrons, therefore here also you have got 10 electrons. In the case of Ng2 plus, same way. I've removed 2 electrons, which will give you a total count of 10 electrons. Got it? So in all these 4 different cation and then the anion, you have got the same electrons into it. Therefore, I can call this one as isoelectronic species. Okay? I can call this one as isoelectronic with an total count of electron that is equal to 10 electrons. Fine. Now, if I have to compare its ionic radius, how will it be? I know the anion has to be greater when compared to that of the cation. Similarly, if you have more electrons dumped into it, then obviously it will be more bulgier when compared to its parent nucleus. Therefore, O2 minus is going to have the greater ionic radii. Then comes the F minus, then comes the Na plus, then comes the Mg2 plus, right? You should know this order. It has to be obvious, right? So here you would have got O2 minus, which has the greater ionic radius, then comes the F minus, then comes the Na plus, finally you would have got Mg2 plus. Okay, so this is how you need to get this ionic radius. Okay, you should know the difference between atomic radius and then the ionic radius. In atomic radius, the atom is neutral. You have got the same positive charge and then the same number of negative charge, but in this situation something is excess. It could either be cation or it could either be anion. That is possible. So that was the case. That is called as ionic radius, right? So for an atom you can find atomic radius, same way you can find the ionic radius. That is possible. Fine. Now finally we are into the last part of the session, which is going to be ionization enthalpy. I have got like 3 different terms to represent this ionization enthalpy. One is ionization enthalpy, then you have got ionization potential, and then ionization energy. So these 3 terms actually represents the same thing. Got it? The name itself suggests we are gonna ionize an atom. So ionizing an atom actually means removing electron from it. So you have got like 2 different terms. One is ionization and the other one is electron gain. Electron gain clearly suggests I'm gonna dump electron into it. Here I have to remove. I have to actually break that bond. I have to break that interaction between the nucleus and then the electron, and I'll have to remove it. Okay. So here what I'm going to do is energy required to remove electron from the gaseous state. Okay. So here generally we will learn this one pretty more in the physics, as if now it should be obvious. Generally there will be the attraction between this positive charge and the electron. Okay, therefore it is going to attract it. So when this electron gets attracted, it will release the energy. Okay, it will release energy to the surrounding and then it will come closer to it. Okay, when you have got like 2 attraction, it will obviously gain velocity. That energy will be released to the outside as photon or any other form, or in the form of heat, whatever it is. It will just get released to the environment. In the situation when an electron is actually added into the atom, the energy will be released. Got it? Then what should be done? If I have to remove this electron from the atom, I actually have to break it from this interaction. So I'll have to give energy to break this electron, right? So here, what's the energy that I need to give to remove an electron from an atom? That has to be in its gaseous state. Okay, so it has to be in its gaseous state or the ion, which means if I remove the first electron, then it becomes the ion. Then if I have to remove the second electron, that's going to be the second ionization enthalpy, right? So whenever an electron comes into the nucleus, it will release energy to the surrounding and it will get bonded to that atom. Same way, if I have to remove that electron from that bond, then I'll have to, from that interaction, then I'll have to give energy to it. Okay, so in this situation, I need to ionize it, which means I have to remove an electron from that atom or ion. So I have to give energy to it, right? So here you have got X that was in atomic state, neutral state. Then I have to make it as a cation, so I have to remove the electron from it. So if I have to remove the electron from it, I just removed one of the electron, and this was in its cation state, in the gaseous state. Okay, got it? So same thing, same logic, same intuition. So here I've taken beryllium, which has beryllium, so which has like 2 electrons in its inner shell. It's hard to remove this electron. Okay, so that is tightly bonded. That too, it's a noble gas configuration of helium. That you have got like 2 valence electrons. Got it? I just need to remove this first electron. That's going to be first ionization enthalpy. Obviously that will be comparatively easier. Then you have got this effective nuclear charge acting on this electron, and then it's going to compress it. Therefore once you remove this one, the removing of the second electron becomes much more harder when compared to the first ionization enthalpy. Okay, therefore second ionization enthalpy will be greater when compared to that of this first ionization enthalpy, right? So here, when I give energy to the electron, when I give energy to the electron, that's going to be positive. Yeah, because I'm just giving an energy to that atom and then I'm just removing it, right? So I am the one who is spending. So therefore it has to be positive. So energy given to the electron will be positive by me will be positive. If it releases energy, that's going to be negative. So that is voluntarily releasing the energy because of the interaction. So that's going to be negative. Okay. See, you will get used to the sign convention in the physics. Okay. So you'll get why am I putting this one to be positive and negative in the physics? As if now you have to remember this one. If I just need to give the if I just need to give the energy to the electron, then I'm just pumping in the energy, therefore it is positive. If it is deliberately giving us the energy outside, when it is getting close to the nucleus, that's gonna be negative, right? So this one has to be clear. Yeah, it is simple, right? When electron is removed from stable atom, we need to give energy. So I just need to give the energy and I'll have to remove it. Therefore, ionization enthalpy is gonna be positive, okay? Right? It has to be clear. Yeah, no doubt should be there with this case. So let us check how will it be across the period and down the group. Across the period, what has happened with respect to the atomic radius? It got shrunk. Okay, as you move across the period, it got shrunk, which means it is, yeah, the interaction between the nucleus and the electron was heavier. Therefore, it will become hard for us to remove, right? So across the period, ionization enthalpy is going to increase. Atomic radius will decrease, but with the case of ionization enthalpy, it is going to get increased. Logic should be clear. Then what should be the case for the down the group? So down the group, the atomic radius got increased, which means the electron is farther away from the nucleus. Therefore, it will be easy for me to remove. Therefore, down the group, ionization enthalpy is gonna decrease. The other way around, right? So this is something that you need to know. I have written that one in the next page. Let me get to it. So that's what I have written it over here. Here you've got across the period. What will happen to the ionization enthalpy? Ionization enthalpy increases. What's the reason? The reason is because electrons are filled in the same shell. Okay, as it is getting filled in the same shell, you have got too much interaction between the outermost electron and the nucleus, right? So here the reason is electrons are filled in the same shell. Okay, so next, down the group. So what is going to happen with respect to down the group? With the case of down the group, ionization enthalpy is going to decrease. Yeah, one of the reason that I could give is, yeah, there is more distance between the outermost electron and then the effective nuclear charge. Therefore it is not going, therefore it is hard for this nuclear charge to give that pull to that outermost electron. Yeah, and by the way also those inner electrons, okay, though not the valence electron, the inner stable noble gas electrons configure those noble configuration electrons is gonna shield those positive charges, isn't it? Therefore you are gonna have more shielding. If you have like more shielding, effective nuclear charge that's going to impact that outermost electron is going to decrease. Okay, so the distance is obviously greater, same way, because it's not able to give such a great impact to that outermost electron, right? Therefore it hasn't shrunk. If it hasn't shrunk, then obviously effective nuclear charge is also less. Okay, yeah, that was the reason why as you move down the group, ionization enthalpy decreases, right? So same intuition, same thinking, nothing more to it. So down the group, what is going to happen is effective nuclear charge is going to decrease. So down the group, effective nuclear charge decreases. Got it? So you will get statement based question. That's why I'm giving you those explanation. Anyway, you should have known this one by the way, isn't it? Next, we will see just one exception to it. With that, this session will get completed, right? The exception that we are gonna see over here will be with respect to the completely filled S subshell and then the half filled P subshell. Got it? So those two stuff I've told you, right? When you have half filled and then the completely filled, that's going to be more stable, right? So when it is more stable, it will be hard for us to remove that electron. Got it? What we expect with respect to across the period is lithium, beryllium, boron. But what we actually see is, we see that boron, with the case of boron, it will be easy for us to remove that outer electron, first electron, when compared to the beryllium. The reason is because with the case of boron, you would have got 2p1, isn't it? You would have got like 2p1. With the case of beryllium, the outermost electron will be from 2s2, right? When you compare these two stuff, 2s2, it will be hard for us to remove when compared to boron, because here it is like fully filled s subshell. Okay, so when you have like, I mean, fully filled s orbital or subshell, whatever it is, yeah. Okay, so here as you have got fully filled s orbital, that's gonna be more stable, right? So yeah, it's fully filled s orbital. That's why this one got flipped. Okay, we know lithium has greater atomic radius, then comes the beryllium, and then comes the boron. So what we expect is boron to have more ionization enthalpy, but that's not how it is. The beryllium has more ionization enthalpy when compared to that of the boron. The reason is because it has fully filled stable s orbital, right? Then after lithium, boron, beryllium, carbon, same way. We expect like nitrogen and then comes the oxygen, but it's gonna be other way around. So here you will get like oxygen. Here you are gonna get the oxygen and then comes the nitrogen. Okay. The reason is because with the case of, yeah, with the case of nitrogen, so it's gonna be like boron, carbon, nitrogen, right? So with the case of nitrogen, you will have like half filled p subshell. Okay. So that's why that two got flipped. So here for the nitrogen, you would have got 2p3. Okay, as you have got like 2p3, that's gonna be more stable. Okay, so because it has attained half filled p subshell, right? So you would have got like p subshell, right? So here I'm just gonna compare these two stuff, which is like oxygen and then the nitrogen. Those two stuff will get flipped. Those two stuff will get flipped. Same way, boron and the beryllium will get flipped. Got it? So it should have been lithium, beryllium, boron, but that's not how it will be. It will be lithium, boron, beryllium. Then comes carbon, nitrogen, oxygen. No. Carbon, oxygen, nitrogen. That's how it's going to get filled, because with the case of beryllium, you have got fully filled s orbital. That's going to be stable. Same way with the case of nitrogen, you have got half filled p subshell, which will be more stable when compared to other fillings. Yeah, same way if you look at the next period, yeah, the third period, there will be this flipping. You would have got like sodium, magnesium, aluminum. It's gonna fill other way around. So you would have got sodium, aluminum, magnesium. Okay, sodium, magnesium, aluminum, silicon, phosphorus, sulfur. That too will be flipped. Therefore, you would have got like sulfur, phosphorus. Okay. Same argument that I've made over there. With the case of phosphorus, you have got like half filled p subshell, that would be preferred. Same way with the case of magnesium, it's like fully filled s subshell, that would be preferred, right? This is what you need to know regarding the ionization enthalpy. Okay, you should be clear with all the concept that I've taught you in this class. So the stuff that I've taught you were the periodic table. How does the element gets arranged in that periodic table? Based on it's like modern periodic table that is based on the Mendeleev arrangement of the elements. Got it? You have to be clear with all those arrangement that I've told you. Same way you should have memorized first 30 elements, and then you should have memorized those S block elements and then the P block elements. You have to be clear with that. Yeah, then we did see the nomenclature for the elements which has atomic number greater than 100. We have seen all those stuff. And then we did see like two important concepts regarding the periodic trends. They were atomic radius and then the ionization enthalpy. Got it? In the case of atomic radius, it is hard for us to get the radius for different metals and then the non-metals. So I'm just going to put a single term, which is atomic radius. For the non-metals, it is possible for us to find the covalent radius. For the metals, I'll have to get the crystal radius. Same way for the noble gas, that's going to be van der Waals radius. Finally, there is something called ionic radius, which I've told you. Yeah, ionic radius exists for all the atoms, right? Depending on the number of electrons that I'm going to fill to it, you'll get different ionic radius. Got it? You have to be clear with that. Finally, we did see the ionization enthalpy. What is meant by ionization enthalpy? You're going to ionize the atom, which means you're going to remove electrons from it. So removing electrons, I have to give energy to remove that electron, right? Whatever energy that I give is going to be positive, right? So generally, ionization enthalpy in all those situations is going to be positive. Got it? Yeah, I'm going to remove it. So I have told you the exception also with respect to the second period and then the third period. Okay. So these are something that we discussed in this class. You have to be clear with all the discussion that I've made. Yeah. With this, the video is completed. Bye.